So we're going to discuss 3/16 tubing, kind of how it got here. We're going to talk about some installation. We're going to talk about some sanitization practices, some different ways of maintaining yield. So, like say, small group. If you got questions, chime in. There's no foolish questions. Like say, jump in whenever you want. So really, by all aspects, today's tubing systems have really become the benchmark of the maple industry by today's standards. So we look at the pros of the tubing system. We're not hanging bags and buckets. We're not storing them in the off season. We get that yield increase by using the tubing in different things. And the initial setup is sometimes cheaper than buying bags and buckets and covers and all that other good stuff. So some of the cons, of course, animal damage to tubing. Out in the woods requires a little more maintenance and a little more time in the woods than buckets. Yields are often reduced, without proper maintenance. The thing is with tubing that you need to remember is we're probably doing about the same amount of work in the woods. We're just doing it at a different time of the year. We're not spending as much time in the woods with it during season, as we are when we're gathering bags and buckets on a daily basis. So when we look at the history of vacuum tubing, it's really been around for quite a while, and it's this original this original research that was done on tubing is really what led to the development of the 3/16 tubing system. So when we look back to the 1950s and 1960s, there was two gentlemen with the U.S. Forest Service by the name of Bob Morrow and Carter Gibbs. And those two gentlemen were the first people to do any research using plastic tubing and putting high numbers of taps on it, introducing vacuum on the system, and documenting a yield increase. So like I say, when we look back to the 1950s, that's kind of when this whole thing got started. So in most cases, when it comes to tubing, we've got 60 to 70 real solid years of good research that we've been able to keep over the years, and that has really driven the tubing systems to where they are today. So now some of this research that they did back in the 50s and 60s is really what drove us to get to the 3/16 tubing. So they were experimenting at that time frame of putting 75 to 100 taps on a 5/16 line, running it down a hill, and they were starting to see some of that natural vacuum, and that natural vacuum was showing that yield increase. So it was some of that early research that really led to where we are today. Not all woods are suitable for a high vacuum tubing system. Topography of the woods may not quite be right. It may be really potholy. Electricity might not be available for that wood lot. Wood lot might not be dense enough. We might not have the taps per acre. That and the size of the sugaring operation may not justify the cost of a mechanical system. Like I say, so there's a reason for the 3/16 tubing out there in the small producer settings, for lack of better terminology. So really, how does that 3/16 tubing work? So when we fill a line full of sap and we trap that sap in that line, it's the weight of that line, the weight of the sap inside that line pulling down, that really creates our natural vacuum, or our vacuum, inside of our system. Um, the minute that we have one leak in that line, though, we lose that vacuum. Where with a traditional high vacuum system or a vacuum pump, we have that external pump there to really, make up for that air loss, or make up for that hole inside of the system. So how do we create tubing with or how do we create vacuum with the 3/16 tubing? Really, one of the things that they did is they looked at that original research from the U.S. Forest Service from the 1950s, and they said, okay, if we shrink the diameter of that line and we can fill that line quicker, what we can do is we can get that column of sap, or that column of liquid pulling down on that tubing. We can fill that line faster. The faster we fill the line, the quicker we can generate vacuum. So really, they reduced the inside diameter of the tubing by 36%. We added more taps per lateral line. We increased the distance, or the length of our lateral lines. And then, like say, we're putting that tubing on the maximum grades that we can possibly find. So that's really kind of how we're making that vacuum with that system. So when we look at 3/16 tubing versus 5/16 tubing, if we put 16 ounces of sap into a 5/16 tubing system, we're going to fill about 1.5 feet of line with 16 ounces of liquid. Okay. Now, if we put that same 16 ounces of sap into a 3/16 line, we're going to fill just about 4 feet of line. Okay. So that really is the difference. That same 16 ounces fills a lot more line and brings us up to a spot where we can start producing vacuum by having that column of liquid pulling down on those taps. Okay, so how much vacuum can we create? So we can make 0.88 inches of vacuum per every 1 foot of elevation change. Okay, so say for example, if we have a hillside that has 10 feet of elevation change from top to bottom, our top tap, we will be able to generate 8.8 inches of vacuum. Okay, so when we look at a tubing system, we really need to have approximately 33 feet of elevation to create 28 inches of vacuum. Okay. Now, when you look at a line running down a hill, so say for example, this is my hillside and this is my line that runs down this hill, our vacuum level in that tubing system changes as we come down the hill. So the very top tap, say for example, I will make my 28.5 or 29 inches of vacuum on the very top tap. Every tap that is downhill from there, I will generate or I will create less vacuum. This is why, for this particular reason, we don't see a lot of 3/16 tubing used in commercial applications. So me as a producer on high vacuum tubing with a mechanical vacuum pump, if these were the taps on my line, say for example, and on a 5/16 line, we would never have this many taps. As I travel down that hill, my vacuum level stays here at 28 inches. Okay. I don't have that decrease. So we do see the yield bump with the 3/16 tubing because we are able to generate, like, say, 29 inches of vacuum up here at the top tap. But when we get down here to say 10 feet, we're only going to have about 8.8 inches of vacuum on that particular tap. So that is really kind of one of the downfalls of the system. The farther we come down the hill toward the discharge point of that 3/16 tubing, the less vacuum that it will create. Okay, system layout. We need to see good vertical drop, from the top to the bottom to generate vacuum. We like to see a minimum of 5 taps on the line is really what we'd like to see. Unfortunately, we don't have any solid university research that says after I get to, say, for example, 25 taps, I start to lose yield. So we really don't have a really good number of, maximum amount of taps on the top side. I've given this 3/16 seminar probably about 7 or 8 times since November in different parts of the country. And a lot of feedback that I'm getting from producers that are running a larger volume of the 3/16 tubing, they're usually saying anywhere from 15 to 20 taps on the top side is where they're finding the best results. Okay. So we're seeing, 5 taps on the bottom side at a minimum to try and get that line filled up with sap. We're going to probably say 15 to 20 taps on the top side is going to be max. I've had some customers that have said, we've had 25, we've had 30, we've had 35 taps on a line, and we did see a little bit of a reduction. I'm going by word of mouth. We don't really have a lot of documented research that really shows this is too many at that point, not like we do with the 5/16 tubing. Length of the lines, we are probably going to recommend right in that 150 to 175 feet range, with about, like, say, 15 to 20 taps on a line. If I have a squirrel chew on a line and I have 15 taps on it, I lose vacuum on 15 taps. I didn't lose vacuum on, 50 taps. So there is a little bit of an advantage to having a fewer less taps on a line, in case we get some animal chews and stuff like that, that we really don't see a reduction on 50 taps versus 15. 3/16 line, into a storage tank or, into a main line, like, say, either way. So that's really what we're seeing on the system layout. Well, and I'm going to say this, it's probably a little bit on the long side, but a lot of it's going to depend on your woods. If you get down in the southern part of the state, down by Cashton and Viroqua, where, we see 175 feet of drop in that 500 feet, it's probably going to be fine. But if you only have 12 or 13 feet, say, for example, on that 500 feet of drop, it's probably going to be a little bit of a lazy flow. So, depending on, like I say, every woods is just a little bit different. So, no, no. And there's some really good research that shows that. And that's why, because even with 50 taps on a 5/16 line, we don't fill it and we don't generate that level of vacuum like we do with the 3/16. So I mean, that research there goes back. So if you have internet access, www.mapleresearch.org. Tim Wilmot was the researcher that did the majority of the research on the 3/16 tubing. And they did some comparisons between 3/16 and 5/16 lines. So if you wanted to reference that research article from Tim Wilmot, you surely could. It is available, like I say, on mapleresearch.org. So, but yeah, we don't see that vacuum bump on that. You know, Even looking back to Bob Morrow and Carter Gibbs' research in the 50s and 60s, even with 100 taps on a 5/16 line, they were only showing vacuum levels of 4 or 5 inches of vacuum, so very low. Nothing like we see with the 3/16. So, okay, when we look at system layout, we really kind of want to avoid this W pattern. When we run down, the woodlot like that, using a W pattern, we have a tendency of using a lot more tubing. when we tube a woods, really kind of by today's standards, we like to try and like say I'm going around this tree here. So we really try to avoid that 180-degree wrap around that tree if we possibly can. Okay. So basically what happens is, when you get into a pattern like this, in Wisconsin, depending on where you live, we put in a lot more tubing a lot straighter than we do in a lot of places because we don't have a lot of grade. And when we start zigzagging through the woods like this, if we don't have a lot of slope, we chew up a lot of grade. Also, like I had mentioned, we're going to put a lot more tubing out in the woods by zigzagging back and forth. So we really like to see this kind of tubing kind of in this lazy S pattern coming down the hillside, versus that, like say, that 180-degree wrap on the tree. So really, what is the killer of our sap? Okay, it is heat. Okay, the quicker I can get that sap out of a tubing system, the better quality of syrup I'm going to make. So when I'm running down the hill in a pattern like this, I can get the sap from the tap hole through the tubing and into the tank very quickly, which is going to decrease the amount of temperature that sap can pick up in the process. So that's the other reason for kind of wanting to run it straighter down the hill as far as that goes. Like I mentioned, that lazy S pattern will use, like say, less sap. We're definitely going to get less heat in that tubing. And like I say, the less sap heating, the better quality of syrup we're definitely going to make. So first off, we need to really kind of know what's going on internally inside the tree. When we look at, what's going on in our 3/16 tubing. So when we go below freezing at night, this tree goes into a state of vacuum. So what happens at that point when we go into that state of vacuum is that tree can develop up to 10 inches of vacuum in the stem of that tree. And what it's doing is it's drawing the sugar from that root system up through the stem of that tree to basically help protect it from the cold. Okay, now when we go back above freezing, we're forcing that sap back down the stem of that tree into that root system. During that particular process, we can generate up to 25 psi inside of that tree. So that's the internal dynamics that's going on inside that tree when the sap is running. So with that being said, like I say, we can create that 10 inches of vacuum here. We can make up to 25 psi here. So we really have a pretty good swing internally inside of that tree from a vacuum level to a pressure level. Okay, first thing we need to do, we need to make sure our 3/16 lines are not in the sap. Okay, what do we know about that tree? That tree, when it goes into a state of vacuum at night, can make up to 10 inches of vacuum. I can actually pull sap from my tank, or a great example of this is a 3/16 line from a single tap running down to a bucket sitting on the ground. The 3/16 line is in the bottom of the bucket. I can actually draw sap out of that bucket and put it back in the tree. Okay, so we always want to make sure that when we are discharging our lines, that they are not below our sap level of our system, or the sap level in our tank. Okay, so let's talk about that drawback in that tubing. Okay, what's going on internally in there? So we mentioned before that we can make up to 10 inches of vacuum internally inside that tree. So when we apply 10 inches of vacuum on a 5/16 line out in the woods, we can draw sap backwards in that system about 12 inches. Okay, now, when that tree goes into a state of 10 inches of vacuum on 3/16 tubing, because of the smaller inside diameter, I can draw back sap in that system approximately 12 feet. Okay, so there is a lot of sap that can be pulled backwards. Once again, like I said, we go back to that 16 ounces of sap and how much, lined that 16 ounces of sap, in a 3/16 line is going to be roughly 4 feet of hose. So as that pulls back, I can move a large volume a great distance with that small inside diameter. So we need to keep that in mind. Okay, so one of the things, to help prevent some of the yield loss in the 3/16 tubing is we have come along with a 3/16 by 3/16 by 5/16 T. So what that allows us to do is that allows us to put a 5/16 drop line onto our 3/16 tubing system. Okay, so what do we know about that 5/16 tubing? We can only move sap roughly back 1 foot. Okay, so if we use a 36 to 42 inch length drop line, and so this is what we're going to be talking about when we talk about drop lines. It's the hose that goes up to our tap that is connected to our 3/16 tubing system. If we use a 36 inch to 42 inch long piece of hose there, and say, for example, here's my 3/16 line, and then my tap is up here, this line usually in a vacuum system is not full of sap. Okay, so at that stage of the game, if I carry a foot of line in that 42 inch long drop line, I'm not going to draw the sap out of my tubing system back into my tap hole. Okay, so a maple tree basically heals itself by using a process called compartmentalization. Okay, so what happens during the process of compartmentalization is every cell that is exposed to that tap hole starts to wall itself off when contamination enters that tap hole. Okay, so this is a tap hole here, this dark circle, this is our tap hole, and this is that compartmentalized wood or that stain streak that we see internally inside the tree. Okay, that wood is still live wood, but the cells have compartmentalized themselves off to the point where they do not conduct sap anymore. So the only place that we're going to see sap moving in this tree is, in this example, is the white wood between our tap holes, or the white wood that's located over here. Okay, so with that being said, we really look at that stain column and we really look at that stain column, and this is what's going on when we put that type of contamination in that hole. Like I said, those cells wall themselves off so that infection won't make it anywhere through the tree. So what happens is we usually stain about twice the width of our tap hole. This is why, as an industry, we've pretty much moved away from the 7/16 taps. So when we did run a 7/16 tap, we would stain a column of wood about an inch wide. We dropped down to that 5/16 tap. We reduced that width, substantially. When we ran the 7/16 taps, we would typically stain 12 inches above and 12 inches below that tap hole. When we started or switched over to the 5/16 tap, we would see about 6 to 8 inches above the tap hole, 6 to 8 inches below the tap hole. So we really reduce the amount of non-functional wood or stained wood that we would put into that tree. When we look at tapping depth, if we're tapping in, say, for example, at 2-inch tapping depth, we stain about an 1/8 inch deeper than the hole, okay? So our stain column will go into that tree about 2 1/8 inches if we're tapping at 2 inches in depth. So that's really kind of like, say, what's going on internally inside of that tree. So when we look at sap drawback, and compartmentalization, I'm a product of the 70s, okay? So when I was a kid growing up, we had a product that was called Sap Flow Tap Flow pellets, okay? We would put one of these pellets into our tap hole, and what it did is it prevented the tree from healing itself, okay? So instead of our stain columns looking like this, our stain columns look like this, okay? So I'm going to be the first one to tell you that I don't want to see sanitizers in my tap hole. I don't want to see sanitizers on my drill bit, okay? First off, alcohol or ethanol are not approved sanitizers in the US by the FDA. And the second thing I don't want to, so I don't want to be using that product, like, say, on the drill bit or in the tap hole because it's a banned product. But overall, or most importantly, we don't want to see this. We don't want to damage our trees. We don't want to interrupt that tree's ability to heal itself. Okay, that is really kind of the key. Okay, so how many people are changing taps on their tubing system every year? Couple, okay. So when we talk about that process of compartmentalization, we're just going to kind of touch back on this again. When we put a brand new tap into that tree that is nice and clean, that tree does not know to heal itself, okay? If I take a tap that's 1, 2, 3, 15 years old, whatever the case may be, the minute that I stick that dirty tap into that tap hole, that's when we see that tree immediately want to start to heal itself, okay? So over the years, we talk about the yield increase from a new tap being around 17%. If you are a hobbyist, say, for example, and you're tapping on bags and buckets and you're running cast aluminum taps or stainless steel taps, they're too expensive to throw away, okay? Sanitize them, make sure we're getting them clean, okay? Same scenario there. The minute that I take that 20-year-old cast aluminum tap and stick it into that tap hole, if that tap hasn't been sanitized, that tree wants to start to heal itself, and we're going to get a lot less sap out of that tap hole. So, okay. So now we're going to talk about microbial contamination and the effects that it has on a 3/16 tubing system. So, what do we know about microbial contamination? So, as our temperatures rise, we really see microbial growth explode once our temperatures get over 50 degrees. Okay? So as our temperatures increase, the amount of microbial load inside of our tubing system just explodes, okay? And that's why typically on a 3/16 tubing system, year one, thing works really good. It works beautiful, okay? Year number 2, we're seeing fairly good yield until we get usually to the tail end of that second year. And then year number 3, if we haven't been changing tees, if we haven't been sanitizing, year number 3 on that 3/16 tubing is quite a tail dragger. It usually crashes pretty hard. Sometimes it plugs to the point where the sap hardly doesn't want to come out of the system, depending on how it was taken care of and how it was maintained. So when we look at, like, say, that temperature effect is, typically on the tail end of season, once our ambient air temperatures start to increase, that's, like, say, when we see the more issues of that biofilm starting to break loose inside that line, flow down the system and get behind some of our tees and some of our fittings. So, going along with that, like I say, later in the season, we get the fermenting of the sugars. When we start to see that sap in the late season or in the tail end of the year, and you go over to your tank and it's got that cloudy or that white appearance or that hazy appearance to that sap, that cloudiness or that white appearance that you're seeing, that's the bodies of yeast and bacteria that have developed in that sap. So as our ambient air temperatures go up, our sap quality usually goes down. Okay, when that sap quality starts to decrease, so does our syrup quality. Usually when that starts to happen, when we get that type of sap in the tank, we usually start to make a little bit darker syrup. Okay. So, and then what happens is essentially our tap holes start to shut down, just a little bit more. So, the best yield on a 3/16 tubing system, like I mentioned, is the first year. The system is clean. There's no microbial contamination. It's ready to run. It works really awesome that first year. Usually, like I said, we start to fail end of that second season. Usually third year, we have a pretty significant reduction to perhaps a system that is fairly plugged. So what happens is we get a lot of what's called biofilm and yeast that grow in the system. Okay. So at the end of year number 2, usually people untap their system, drain everything out of the system. What happens throughout the summer months when we take the moisture away from that biofilm and that yeast is it kind of dries up. It kind of, like for lack of better terminology, shrivels up as it's inside the system. The minute that is rehydrated with sap, it just starts to expand and kind of start growing again. So what happens at that stage of the game is you can look at that system, say for example, in June or July when the system is completely dried out. You'll look into your fittings and say, hey, this thing looks pretty good yet. I don't know what everybody's talking about. It looks like it's going to be fine. Like say the minute that we cut that tea out of that line, throw it in a container of water, pull it out and look at it, that biofilm will just kind of expand and grow, and it'll kind of swell that fitting right shut. So that's the issue that we have with 3/16 tubing that we don't have with 5/16 tubing. In 5/16 tubing, all that material kind of passes right straight through the system. We don't build it up or back it up behind the fittings. So when we look at the tubing itself, this is that excuse me, that biofilm that we start to see come down and start to back up behind our fittings. Okay. Now, like I say, throughout the summer months, when this stuff, like I say, starts to shrink up as the system starts to dry out, if we left our taps out of the trees and just left them hang, this stuff will kind of skinny right up, and you'll think, yep, we're not going to have any problem. But like say, the minute that it rehydrates, we're gonna have some issues. So how can we maintain our yields? So, like I say, tea and fitting replacement is kind of one of the keys, unless you're going to replace all of the 3/16 tubing. Okay, so usually what we're recommending to a lot of our customers is after the second season, we want to replace any connectors, we want to replace any tees, we want to get those tees and connectors that are filled with biofilm, get them out of the system, and put some new fittings into the system. Like I had mentioned before, new tap every year. Okay, we want to make sure that we put that new tap into that tap hole. We keep it clean. We maintain our yields that way. Another thought is, color of your tap. Depending on what tap you're using, typically the white taps keep our tap hole the coolest. Okay, that there, we see a little increase in sap production with that white tap because we keep the tap hole colder. We don't get it much over 50 degrees on most days, so we're not growing that biofilm and that bacteria rapidly once we get over 50 degrees. Me as a commercial producer, I am on a drop line replacement program at my place, even though I'm not on 3/16 tubing. So what we do is we replace the drop lines every 3 years. So when we look at the microbial contamination in that first 3 feet of your tubing system, that is the first 3 feet of tubing that is closest to your tap hole. Okay, how clean that tubing is going to directly affect your yield. Okay, the dirtier that first 3 feet of tubing is, the lower your yields are going to go. So we found, and there's good university research that backs this up, is if we change that drop line every 3 years and we manage that microbial contamination in that first 3 feet of hose, we can actually maintain our yields fairly well. So I'm going to be the first to tell you that I have some tubing in my woods that is probably 14 years old. And we're running a new tap every year, and we're running a 3-year drop line replacement. And I'm hanging with, my yields are hanging with systems that are probably 3 and 4 years old. So for me as a producer looking at that yield, I'm kind of hitting the home run ball because I've got some tubing out there that's fairly old. Now, granted, that is a 5/16 system on high vacuum versus a 3/16. So the two are a little bit different, but the same thing holds true with that, that first 3 feet of hose. The cleaner that we keep that first 3 feet of tubing, the less chance we have of contaminating that tap hole. Yes.
You change the taps every year. I think you guys here, we learned that a couple of years ago.
Okay.
What about the fittings? Every year or
Probably about every other year in a 3/16 system. Now, there's a little caveat that goes with that, and we're going to talk about that a little bit more, is sanitizing with bleach. So how many people are out there are sanitizing their 3/16 tubing? Couple. Okay, I'm not going to try and pick on anybody. When are you sanitizing? Okay, season's done. Anybody else? Okay, beautiful. Okay. So when we talk about sanitizing with bleach, timing is the key. Okay. So what do we know about microbial growth? Microbial growth explodes when it's over 50 degrees. Okay. So if I sanitize, say, May 1st, okay, my microbial contamination level is here on the 1st of May. I sanitize May 1st. My microbial load inside of my tubing system drops down to here. Okay. What happens over the summer? It's hot. And that contamination grows and it grows and it grows and it grows and it grows. And by the time I get to September, it's like I didn't really do much. Okay. So when we look at sanitizing, especially with 3/16 tubing, let's look at timing. Let's sanitize that tubing in the fall, late fall, just before it freezes up. Okay. What's going on? Our temperatures are a lot lower. Okay. So we will not grow that microbial contamination. We will not grow that biofilm because our temperatures are relatively low. So I've got my tubing system extremely clean prior to the cold weather and the fact that it can't grow anything. So by the time spring comes around, I got a system that's in really good shape. Okay. So it's just a little bit of timing change to what one would think they should be doing. And it's just like say, it's based on how the material grows throughout the summer. So if I am going to sanitize with a bleach material, I want to make sure that I am using a calcium-based bleach. Okay. So what is a calcium-based bleach? Calcium-based bleach is what we call calcium hypochlorite. Okay. That is the bleach that we would recommend for tubing cleaning. Now, household bleach is sodium hypochlorite. Okay. So when we talk about sodium-based bleaches, when that bleach degrades, it salts out. It creates, in essence, it creates salt or sodium when it degrades. So if we use that regular household bleach, that sodium hypochlorite, all the critters in your woods are going to think you put a giant salt lick out there. Okay. And they will eat you out of house and home. The nice thing with calcium-based bleach is, like, say, it's a calcium base. It doesn't salt out. It doesn't attract the rodents. Now, where do I find it is the next question we always get. So the calcium-based bleach is commonly referred to in the industry as what we call pool shock. Okay? And pool shock is meant to sanitize porous surfaces. Okay? Tubing, when you look at it under a microscope, is actually porous, and that is a good porous surface sanitizer. So you're going to look for a pool shock material. Now, when you mix this material, we're not sanitizing a pool. We're sanitizing our tubing system. We have a lot of garbage in our tubing system. Okay. So we want to make sure that our mix ratio is really between 400 and 600 parts per million on our water mix. Okay. That's how strong we need to make the bleach to make it effective. So what do we know about sanitizers? It's not only the concentration level of the sanitizer, it's the contact time. Okay, so when we put that sanitizer into our tubing system, we need time for that chemical to interact with that biofilm and that bacteria and that yeast inside that system to actually start to break it down and degrade it, shrink it up, and break it up to the point where we can flush it out of the system. So at least 20 minutes to 30 minutes of contact time, we want that liquid inside that tubing system. Okay. And it's really important. I had a question in yesterday's seminar. How important is it that we fill that drop line up? Well, like I had mentioned, from a sanitation point of view, that is the first 3 feet of hose that is away from your tap hole. The cleaner I keep that first 3 feet of my tubing system, the better my yields are going to be. So we definitely want to make sure that we keep that liquid in that drop line for that period of 20 to 30 minutes before we start with the water flush. So with that being said, we need to make sure once we are finished with the sanitizer, once it had the appropriate contact time, we do get that material washed out of that tubing system or rinsed out of that tubing system before we basically end our process. Okay, so it really is important we get it rinsed out of there. Just a reminder that, isopropyl alcohol is not an approved tubing sanitizer here in the US. It is a banned substance by the FDA, so we cannot be using isopropyl alcohol inside of our tubing systems.